Yeah, thanks everybody for showing up, and thanks Arthur for inviting me. I'm really happy to be here. And yeah, so my talk is basically, I want a good parallel language. And it's a follow-up to a talk that I did about 1.5 years ago. I gave a talk at UC Santa Cruz last spring. And that also, there's a blog post on that about me wanting a good parallel computer. And so this is really complementary to that. Like, I still want a good parallel computer. It hasn't happened in the last 1.5 years. And the central thesis, I'm not going to, there's places where the talks intersect. But the central thesis of that talk is that there's a missing piece, which is that you need to be able to do dynamic scheduling as opposed to batch scheduling at this sort of medium granularity. I'm going to talk about granularity. I'm going to talk about kind of the programming language sizes. And by the way, this should be a conversation. Like if anybody has any questions at any point, just pop up and I'd be really happy to take it. So needing to program parallel computers has been an issue for a very long time. I mean, this is BALISP. So the Connection Machine from the mid-'80s was a really ambitious attempt to create a parallel computer. There are large-scale parallel computers, the ILIAC, from even earlier than that. But the Connection Machine was a really ambitious plan to step up the amount of parallelism that's available. So this machine had up to 64K threads, which is still a lot, even by modern standards. Like once you get into kind of huge, data center GPUs, you can get more threads than that. But like your GPU in your high-end gaming machine is, tens of thousands of threads. It's about the same. So this question of granularity is really going to be central to what I'm talking about today. And there's actually a lot of different languages. Like one of the challenges of giving this talk is that, there's GPU language, there's language that people, historical, people in the high performance community use different language. So this is all, it's the same picture, but you use different language to describe the concept. And so you have this hierarchy, right, where you have submissions, which are huge. They can be multiple tens of milliseconds or seconds or something like that. And then you've got dispatches, which are typically less than a millisecond, 100 microseconds, something like that. And then you go down into work groups, which are basically blocks of about 1,000 threads. And those share about 32 kilobytes of work group shared memory. And then you get into subgroups, which are also SIMD vectors. There's like lots of different, or they're warps if you're in NVIDIA land, but it's all the same concept, right? It's basically saying, here's a vector of some number of threads or lanes that are being executed in lockstep parallelism. And then you go down to the lowest level of granularity. You don't go any deeper than this unless, you don't do individual bits, right? Certainly, the Connection Machine did, but that was a long time ago. So you've got this hierarchy of granularity. Question?
Yeah, so what's the application domain besides graphics and machine learning? Where would we be using this kind of parallelism?
Yeah, the question is, what is the application domain? Like, obviously we know that in graphics and machine learning that there's a lot of use for parallelism. My goal is general purpose computing, right? And I mean, I have a specific application that I'm personally very invested in, which is rendering of 2D graphics, which is kind of halfway between kind of traditional 3D graphics that has very obvious parallelism and, and kind of more CPU tasks, because you have a lot of interesting structure. Like you've got a tree of blend nodes. And so, it's not just data parallelism. But I am interested, and if you look at the Good Parallel Computer talk, I go into this a little bit where I classify into embarrassing parallelism, and then kind of interesting parallelism, and then kind of, give up. It can't really be done in parallel. But part of my thesis is there's a lot of really interesting problems out there that are not done parallel today, but could be and should be. And I'm actually going to get into that a little bit in the rest of the talk. Thanks for the question. So this is another picture of talking about kind of granularity and why it's such a problem in traditional, your kind of classic GPU model, that you've got a dispatch where all of the dispatch, like all of the sizes of these 3D grids have to be decided up front at the time that you launch it. You're not dynamically being able to launch, individual dispatches or ideally individual work groups. That's really what I want. Like my definition of the good parallel computer is something that looks a lot like a GPU, but has this missing piece added of, can I launch a work group dynamically? Can I say, I've got the inputs that I need, and I know that, maybe there's sparsity, maybe there's some computation of deciding what to launch, and then I launch it. But in the traditional GPU model, you don't have that you make this dispatch up front, and you say, here are these cubicle grids, and we're going to launch them, and between them live these pipeline barriers, which are basically stop the entire GPU, flush all of the caches, and then start the next dispatch after that. So this picture also gives you a little picture of the different levels of granularity involved in one of these dispatches. This picture works really well for 3D graphics workloads where you're just throwing a million triangles at the screen and then the triangles turn into millions and millions of pixels. And it also works really well for AI workloads, that these big cubicle blocks are big, giant tensors with billions of elements. So it depends on the workload. If you're doing something sparser or more dynamic, this is not going to work well. But there are also a lot of workloads or embarrassing parallelism where this picture is fine. So this is a little bit of a chicken and egg problem. Like if we warped through an alternate dimension and a good parallel computer just dropped right here, we would not be able to program it. We would not have a programming language that would be effective in running on that computer. Conversely, if somebody just invented a brilliant new programming language that fulfilled all of my requirements of what I want from a good parallel programming language, what would you run it on? You could run it on a multi-core CPU, and that would be a good way of testing out the ideas, validating that it's a good language, but you wouldn't be able to get that huge performance throughput advantage that GPUs have. A GPU is typically going to be about 10 times more throughput per dollar or per watt, which is the same thing, than a multi-core CPU. So, I talked about warping through an alternate universe. Like that alternate universe is the one where the Intel Larrabee project from about 15 years ago succeeded. And, that Intel was actually competent. I know it's an alternate universe, and, and maybe NVIDIA stumbled, but it's plausible, right? That if you read the paper on Larrabee, it was a very compelling vision, and that project had a lot of really dramatic advantages. That, the Larrabee architecture was essentially, it looked a lot like a PC today, a lot of cores, each one has a lot of bits of SIMD width. And then when you're talking about this problem of doing the scheduling and the granularity, those problems are basically solved. Those problems basically go away because they're just ordinary computers, and you can use ordinary programming languages. And your memory model is the Intel standard memory model. All of these things that are incredibly challenging and difficult today in that world would just kind of work. And I believe that if that had happened in this alternate universe, that we would have seen an evolution of tools, that you wouldn't just run your kind of standard graphics workloads and machine learning workloads on it, but it's like, oh, wow, we have this machine that has all these capabilities. Let's build programming languages. Let's figure out what workloads we can run on this computer to really take advantage of that hardware. But we're not in that universe. So let's see what we can do. There have been, this field of trying to program parallel computers has been around for a very long time, decades. And so I'm going to kind of start with a very high level survey. There's a lot more depth here of, what are the languages that are out there that have some hope of actually addressing one of these highly parallel computers. And I think, the granddaddy of them is the array languages, of which APL is the exemplar. And, APL, I have a slide on each. I'm not going to go into all the detail here, but I think one of the interesting things about these array languages is that they, even though they're very niche, like very, very few people actually program in APL, but a lot of their legacy is continued on into NumPy and PyTorch, which of course are, burning a large fraction of the carbon that's going into the atmosphere. Another language that is very relevant for programming these parallel computers is CUDA. the, and CUDA is essentially C++, where you have tons and tons of threads, tens of thousands of threads typically, and then you've got hardware, you've got a runtime that is running those on this parallel hardware. You've got a lot of the really interesting work, like, what to watch, like what might be the seeds of the future is in functional languages. And in particular, there is this one called Futhark, which is an ML variant, but it has been adapted to run in parallel, runs on OpenCL, and there have been some really interesting programs written in Futhark, and I'm going to talk about that a little bit. And then I think one of the more interesting recent developments, and we've seen, even in the last year and a half since my last talk in this series, that you have this MLIR project, and there's a lot of projects. It's a very complex ecosystem, and there's languages, and there's runtimes, and there's frameworks that are being built on MLIR, but it is gaining a lot of momentum, and there is a possibility that this somehow is going to evolve into the kind of thing that I want. But there are missing pieces, and I'm going to go into that as well. Clarification.
Are you imagining that the programmer, person with the problem, the programmer or some involved, knows essentially how to parallelize it and then wants to use the language to do that? Or are you talking about something more like an optimizing compiler that knows the hardware and you give it the problem and then it figures out?
Yeah, so the question, I'm going to paraphrase it quickly. The question is basically, does the programmer have explicit control over the hardware, over the parallelism that's in hardware in my fantasy language, or is there kind of like a sufficiently smart compiler that takes your problem, which is going to be expressed in some very abstract way, and says, here's the parallelism in that problem. Let me extract it and map it to the hardware in a way that, the compiler might know more about it. Both are very interesting and relevant approaches, right? And certainly, like, for example, in the machine learning world, you see typically a lot more of the latter, that you're going to express your tensors, that you're going to multiply and all these things, and you're going to throw it at this compiler that's going to do a lot of optimization, like fusing blocks together that can be fused together and splitting it into chunks that are the right size for the hardware. And the programmer generally, if you're an AI researcher, you generally don't want to be thinking to yourself, oh, my work group size is, this many threads and I have this much shared memory. But there are other things where I think the explicit control is really important. And I am going to talk about that.
So StarList fit into?
The question is, where does StarList fit in? And the answer is on the next page after this one. How did I know that this was going to come up in a BALISP meeting? All right. Okay. So where were we? Array languages. Is that where we were? Yes, array languages, right? So this is a sort of APL family. And, there's good things about them and bad things about them. And the good thing is that they are concise. As a matter of fact, that's one of the bad things. That, like, you look at some APL code and you're like, this just, it looks like just a soup of symbols, right? But you do have a rich set of array primitives, and those array primitives, array primitives are a large chunk of what you want to run on these machines. Like, again, in the sort of machine learning world, it is mostly array primitives. And you can sort of imagine, again, one of these alternate universes in which APL evolved into the language that AI researchers used, just because it's very good at these arrays. But APL itself, is a pretty clunky language. There are reasons why it's not very popular. And I think, you can really think of it that there's an under language which is expressing like control flow and how do you structure your program into modules and, where are the abstraction boundaries. And that under language in APL is like really clunky and old-fashioned, and it doesn't have any kind of type system that works for you. And it's also, I think, one of the reasons why it hasn't really, you don't see a lot of popular implementations of APL for GPUs is that the under language is extremely sequential. It's like, do this thing and then do that thing, and the thing might be a very large array, but it might not be. So if you've got, it's again a granularity problem, that if you're trying to do a lot of operations, then APL is going to be sequentializing those, where maybe there actually is parallelism that you can exploit. So as I said, like you can really think of NumPy as being APL without the concise syntax, a little bit more readable syntax, and with Python as the underlanguage instead of this kind of, oddball structure that APL has. And of course, Python is, very, very pleasant underlying. Not perfect. And, one of the things about Python is that it really forces you do not want to do per item operations in Python. You have to structure it all in these kind of bulk things. I want to do something on this million-sized array. So I think, array languages have been a really important piece in the evolution, but they do not represent the future. StarLisp. So StarLisp was a really interesting artifact from this world. And, I researched into it, for making this talk. And the programming model, like this is really the fundamental question is like, what is the execution model that this hardware is giving you? And the programming model of StarLisp is that you basically have one sequential machine, and that's running Lisp. And then you've got this big giant array processor, which you can model as just SIMD with a huge number of lanes in it. That's not exactly true, but that's the closest thing if you're going to map it to what, the kind of programming models and execution models of systems today. So StarLisp had arrays as built-in, data types that in addition to like atoms and concells, you have arrays of big giant, big giant arrays of numbers. And then you've got all of your data parallel operations. So if you want to multiply two arrays together or do any of that stuff, then all that stuff just works. So that's actually, that part of it is actually not that different than NumPy. And when you look at programs written in StarLisp, there's a certain, Python has Lisp roots, right? Python is kind of an acceptable Lisp. And so those programs, those StarLisp programs actually look pretty similar to NumPy programs. One of the things that is most fascinating to me about StarLisp is, I talk about abstraction and support for abstraction, and Lisp has amazingly good support for abstraction. That's its strength. That's the lambda symbol that exemplifies Lisp. And StarLisp with the parallel processing carried that as well. That it has this scan bang bang built-in function, and that does prefix sum. And one of the really, really interesting things about it is that that is not just a prefix sum of some small set of built-in operations, but it takes a lambda. I don't know the answer to how efficiently that was implemented in parallel. That is kind of maybe something to dig into a little bit deeper. But certainly in terms of the language, which is what I'm talking about, that you had the ability to express, I want a scan operation, I want a monoid, prefix sum, generally scan over some arbitrary user-defined function. That is something, so APL has a scan primitive, it's slash or backslash, one of them is reduced and the other scan. And that can take an arbitrary function, but this is a problem with the APL that it basically has sequential semantics. It doesn't say, oh, I can parallelize this. Question?
What's the difference between reduce and scan?
What is the difference between reduce and scan? So they're both operations that do some associative operator on a sequence. And the difference simply is that reduce is the end. It's just adding, like if it's sum, it's just adding all the numbers and giving you one number at the end. Whereas scan gives you all of the intermediate results. It gives you the sequence of basically the running sum. And both of them can be parallelized. That's kind of one of the real advances in the computer science of all this stuff. This was done by Blalock in the 90s, and there's some work that led up to that. So that's going to be a cornerstone. The ability to run these kind of, I call them, I talk about monoids a lot, right? These monoid operations is really central. Okay, great. Right. So another thing that you see in this world is shader languages. And do I have a love-hate relationship with shader languages? Because I'm trying to do graphics, so it makes to a large extent it makes sense. But actually trying to do advanced computation in shader languages is extremely painful. So the programming model here is a different direction than APL and StarLisp, which both have this concept of these large vector types. And in a shader language, you're really dealing with scalars. And so this is implicit SIMD. So you're not explicitly writing in terms of SIMD. You're just saying, here's some calculation, some scalar calculation over scalar types, but I want 1 million copies of this. And then it's up to the language and the runtime and the hardware to group those into SIMD. So if you're going to analyze the performance of these things, you have to be thinking about how did my stuff, how did my scalar threads get grouped into these SIMD blocks, and is that done in an efficient way? But that's kind of hidden from you. That's kind of abstracted from you. So these shader languages are derived from C. CG is kind of the missing link between, from the original C to like HLSL and then today slang. And they're terrible languages. Like, it really makes you wish for the modernness and programmer friendliness of C, right? But there's a lot of other bad things to say about these things, that they tend to be really poorly specified and with a memory model that's really complicated and confusing. So if you're trying to do like sophisticated synchronization, because I've done a lot of things, where you're really trying to coordinate programs, and you're like, are these two data, these two accesses to memory, are they going to race, or are they properly synchronized? And just answering that question, like, does the spec tell you whether these things are synchronized, is it's PhD level stuff. But there is progress, and this is again a lot of progress that's happened in the last year and a half. That there's a lot of very old legacy clunky shader languages, but there's this new one called Slang, which is from NVIDIA, but it's open source, and I think it's actually I think Kronos is actually involved in the standardization of Slang these days, and it is bringing it into the 20th century. It's almost as good as programming in C, and in some ways better. No. The question was, did I mean 21st century? And I am. That is the joke, that that shader languages are still incredibly primitive. Although I don't want to beat up on Slang. Like, Slang has modules. Slang has what in Haskell is known as type classes, and what in Rust is known as traits. It has abstraction primitives, which are just brutally missing from CG and GLSL and those shader languages in that class. And the high level stuff is also missing in Wigzel, which is the web GPU shader language.
So you're saying this promising effort isn't even bringing it into something reasonably modern?
Yeah, the question is, does Slang bring it into something that's reasonably modern? And the answer is, I would say, not quite. And that, again, that's that chicken and egg problem. That the problem isn't the Slang programming language. The problem is the execution model of the GPU that it's running. You're still running as a shader. You're still running in these kind of blocks that where you don't have dynamic control. And Slang, you just can't fix that problem by, you could be the most brilliant language designer in the world, and you still can't fix that problem. So I would make the case that Slang running, through graphics APIs is still very, very far away from what I would consider a good parallel language. Great. So this gets a little bit to this implicit versus explicit, and I want to talk about SIMD. And so we're kind of leaving the fancy hardware behind, and this is a discussion that makes sense on essentially all modern CPUs. There was a time, a long time ago, that CPUs did not have SIMD, but basically they all do now. And SIMD, just so people, it's single instruction, multiple data, and it basically means that you've got assembly language instructions that are running on the hardware, that instead of operating on a single scalar value, they're operating on vectors, which can be in width, typically anywhere from 4 to 64 elements in that vector, just to give you a feeling of that granularity. So when you're looking at SIMD from a programming, so you've got hardware, you've got an assembly language instruction that says add these two vectors together, or conditionally move things from one vector to another based on a mask, right? Those are the kinds of instructions you get in SIMD. But how do you program them? And there isn't real strong consensus on how you do this. And there's really two approaches that are very different. And the first is implicit SIMD, where the programming model is that you've got a lot of threads. They're not real threads. They're kind of simulated threads, but your programming model is you've got a lot of threads, and each one of those threads is operating on scalar types. And then your compiler and your hardware conspire together to take those threads and bundle them into SIMD. And then you're running, that's what the hardware is running as these SIMD operations. And one of the things, so if you've got scalar programs, it might say, if condition, then do A, else B. Well, how does that work if you've got a lot of threads that are doing that if? And the way that it is done is that it's simulated with this concept called predication, which basically says, take your condition, and if it's all false, then you do B. And if it's all true, then you do A. And if it's a little bit of each, right, then you do A with only the true bits masked, and then you do B with only the false bits masked. And that's called predication. And it leads to this concern that, you want to avoid that case. That's called divergence, where your control flow kind of diverges. When the threads are masked out, then they're not moving the problem forward. Your utilization goes down when you have divergence. So you want to be aware of that, and you want to avoid it. The implicit SIMD model, like one of the things that just kind of doesn't work is function pointers. Because when you have if then, you can express, okay, this is what's happening, and it maps in a reasonably, reasonably performant way. But if you've got function pointers, now you've got a vector of, let's say 32 items, and each has a function pointer. It's like, what do you do now, right? And there are answers to this. Like, it isn't a complete showstopper, but it is a fundamental limitation of this execution model that if those function pointers are going to support the kinds of abstractions that you need, like usually you're not programming in terms of the pointers directly, you're doing a virtual function call in an object-oriented language or, something like that. But the model, it's an impedance mismatch between wanting that abstraction and the hardware being able to do it. And then, the last thing is, it's one thing to say, okay, you've got all these threads that are independent, that are just computing the same scalar computation, just replicated many times. But a lot of these problems, you have to do coordination between the threads, and you do have shuffle intrinsics in shader languages. You have a way of saying, I know that there's going to be, typically in a GPU, I know that there's going to be 32 threads that are going to be allocated to the same SM, and you can say, shuffle or do other communication between those threads with these shuffle intrinsics. So the explicit programming model, explicit SIMD, is the other way, where it really is just a sequential program. So you really have the same execution model, the same programming model as you did when you were just adding numbers, but now you're not adding one number, you're adding a vector of numbers, or you're doing other things. So you've got a lot of intrinsics, you've got, in many cases, thousands of instructions, actually. Like you talk about RISC versus CISC, and, ARM, a modern ARM processor, like in this phone, can only be considered RISC. I mean, it just blows RISC out of the water because there's thousands of different SIMD instructions that represent the different types and vector sizes and, all the different combinations. You get into a combinatorial explosion very quickly. So one of the things that I like about explicit SIMD is that your control flow works just like a regular scalar language. So you can have a function pointer, and it's fine because you've basically got one thread of control as opposed to having a different thread of control for each of the lanes in the SIMD. You just have to think about, I'm not just doing this operation on one value. Like one of the problems I want to solve is color conversions. And so the idea of having a trait, an interface, a virtual interface that says, do this conversion from one color space to the other, it's great. You take a vector of 32 colors and you just, you say, I don't know what color conversion I want to do, but I've got a function pointer. I'm just going to call into that and I'm going to get 32 colors back. Great. So the advantages and disadvantages, that I think one of the reasons implicit SIMD, a lot more people write implicit SIMD than explicit SIMD. There's both, but implicit SIMD is really popular because all GPU shaders are written in this model. And I think one of the reasons is you don't really need to invent a lot of new stuff. You can start with C and just kind of extend it and add some of these intrinsics to it, and that has worked, right? That you can get started. You can go to shader toy and start writing shaders without having to learn a lot of new stuff. Yeah, I mean, explicit SIMD has these portability issues that these intrinsics, like the intrinsics for ARM and the intrinsics for Intel, are extremely different, right? They're not just different spellings of the same concepts. In some cases, the concepts are different. Like, for example, ARM has these load and store operations with permutations built in, whereas on Intel, you just have to do, normal load and store and then do your permutations separately. So it's really challenging to do explicit SIMD in that way. And then one of the other nice things, like sometimes you have a vector and it has like, it's not a multiple of 32 elements, it's like 13. And in implicit SIMD with this predication, you use the same predication just to say, okay, now you've got a bit mask of the first 13 are turned on. And you don't have to write code. When you're writing explicit SIMD, you have to say, okay, here's one code that's handling the even sized chunks and then a little bit of code at the end to clean up. And it's really annoying. So that's an advantage of implicit SIMD. The disadvantage of implicit SIMD, I think the biggest one, there's like a lot, but I mentioned the function pointers; those don't work. I mentioned that reasoning about performance is hard because you've got this abstraction of what the compiler is doing that's a little hard to predict. Like, there's actually a lot. If you go into the web GPU, they're trying to define this concept of reconvergence, where you have divergence. When do those threads come back together again? And like that's poorly defined. And there were a lot of experiments that were done on existing implementations, and it turned out that there's all kinds of different behavior. It's very difficult to predict, very difficult to reason about. But I think the core advantage of explicit SIMD over implicit SIMD is that not all of the data types that you're operating on are the same size. And so it's very common to say, I've got 128 bits, but is that 4 floats or 16 bytes? And depending on what you're doing, like if you're just doing matrix multiplies, then you're like, okay, they're all the same size. But a lot of what I'm doing, like I might, for example, load an 8-bit RGB color and then want to do more color computations with 16 bits. So I want to freely mix between different sizes. And when I'm doing explicit SIMD, I have control over that. I can say, here are 32-bit float values. It's going to be a vector of 4 that I'm operating on. And, I might have very sophisticated scheduling where, I might do twice as many operations, on 32-bit values that, twice as many operations per kind of unit per step in the program on 16-bit values as I would be on 32-bit values. And if you think about how do you do that mapping in an implicit SIMD, model, I think it doesn't really work. Like, it's what happens in practice is that you express some number of threads and then the compiler, the sufficiently smart compiler, opportunistically says, oh, there's 2 16-bit operations that I can combine, but you're dependent on the compiler. It's very difficult to predict that that's going to happen. Question?
What I really worry about in ever programming at this level, whether it's implicit or explicit SIMD, is you pointed out that LISP lambda was the ultimate abstraction, basically.
Right.
Every time you have a lambda, you're basically doing an implicit stack push.
That's right.
And a stack push is implicitly a communication to the vector processor.
That's right.
So if you're not careful, if you don't know what's going on, or the compiler doesn't know what's going on, it's going to constantly be floating and unloading the GPU and losing all of your advantage.
That's right. So basically the concern about the implicit SIMD programming model is that it's a very big impedance mismatch with languages like Lisp, where you have abstraction, which is being executed as these function calls, which may be virtual function calls, and you lose that one-to-one. You lose the ability for the hardware to like really understand what's going on. That's right. Yes, that's right. That the stack, there's actually a bunch of problems. The stack is communication, but the other problem that you have with stacks on GPUs is that the stack is variable size, and it might force an allocation to happen, which is something that GPUs deal with very poorly. So in practice, like you're going to hate this, most implementations of implicit SIMD address this problem by just inlining everything. And, and I mean, you can think about like now you don't have to worry about, you're not allowed, typically you're not allowed to do recursive calls. So I listed function pointers, but function pointers and recursion are in the same boat, right? So no, that in general recursion is forbidden in these shader languages for exactly that reason. And I mean, unroll everything, this is again some of the change that's happening is that just for historical reasons, shaders used to be really small. They used to be like a few dozen lines of code, and you could use some lighting thing and some matrix for your transforms, and you compute reflectance, Fresnel coefficients, function shading, and then you output color at the end. But these days, shaders can be thousands, often thousands of lines of code. And if you have something that's built up, from abstractions, then if you inline everything, then it can lead to like huge blowups. And so that is definitely an advantage of the explicit SIMD approach over the implicit SIMD approach, that it doesn't scale to what we're used to on the CPU, where you can have these large towers of abstractions, recursion, all that stuff just kind of works. All right. So I want to talk a little bit about like one of the kind of sub facets of I want a good parallel language is I want a language in which I can write explicit SIMD and I can express my ideas and have that compile portably and run on different machines. And we're not quite there yet. We're making really good progress. And so historically, you would just write assembly code. And I've done a lot of that. And you would do that because performance was absolutely critical. And if you go back 20 years, that compilers, if you even if the compiler had intrinsics, that you would write some code with intrinsics and you'd look at the generated assembly code and you'd say, I can do better than that. But LLVM is very good these days. Like LLVM has advanced dramatically in the last, I mean, it's a very long scale project. And these days, if you're writing code that, I'll give you an example that is one of my favorites, that you've got Boolean operations by, OR and 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 XOR. And some machines like the 88512, the newest Intel stuff, has this really brilliant instruction called VP turn log, which is vector parallel ternary logic. And it can do any 3-argument binary function, any 3-argument Boolean function. And an LLVM is very smart at this. So if you write, A and B or A and not C, which is, like select or something like that, it'll be like, hey, that just reduces to one VP turn log instruction. So these days, you want to be writing, at the very least, in these intrinsics, and then use your LLVM-based compiler to map those to the actual instructions. So it'll do an excellent job. But there's still this portability problem because the intrinsics on Intel are not the same as the intrinsics on ARM. The intrinsics that you get when you're doing WASM are kind of a lowest common denominator subset of those. And so if you're just writing intrinsics, that hasn't fully solved your problem. So the current generation, like if you want to do explicit if you want to do explicit SIMD programming today, what you really want is an abstraction library. And the most mature one is Highway, which was done at Google in C++, and it was used as part of the JPEG XL codecs. And incidentally, multimedia code, you're asked, what are the really good applications for SIMD? And the multimedia codecs are a brilliant application for SIMD because, first of all, you're doing bulk operations. You're not just operating on individual pixels or individual audio samples. You're always operating on chunks. But multimedia codecs also often have a lot of structure. Like, if, it isn't just one operation applied to the whole screen. You have individual blocks, and some of them may have motion, and some of them may have, different transforms that are being applied. And so you do have this need to do this fine-grained or medium-grained scheduling. And in SIMD, you can do that. Whereas, people are not writing shader code to do media codecs. And there's a reason for that. So the JPEG XL project, the people that did that project also built Highway, and it's really successful, really mature, and you can write essentially C++. It's kind of like a DSL embedded in C++. It uses templates a lot for good and bad, but you can express your concept. Like you can write code and then have that compiled portably to high performance code that runs on lots and lots of different chips, and that's shipping at scale. So the Fearless SIMD project, which is something that I've been involved in, is basically an attempt to do highway for Rust. And, very similar concepts where you have a set of operations that are defined, and then those are mapped to the intrinsics that are then going to get compiled, by Rust LLVM. And we have been, it's still in kind of experimental phase, but it's at the point where we're seeing really, really good results. So we have this, we have many different spins on the Velo rendering, the 2D renderer that I've been working on for years now. And one of the more recent evolutions is that we have a version that runs entirely on the CPU, and it makes extremely extensive use of a SIMD, and it's written in this portable library. And we are seeing good results. So that is an existence proof that you can get good results. And so if you have a problem that is suitable for explicit SIMD and you like Rust, then I suggest you check it out. Question?
So how does this compare to like Torch? I mean, I guess it's a slightly different application domain, but where's the Torch C++ library?
Yeah, the question, how does it compare to Torch? I don't know Torch off the top of my head. There, I picked these as examples. There are like a bunch, right? And like in Rustland, there's also Pulp and Wide and the portable SIMD project. So, I don't want to just ring one bell. And I know that there's a half a dozen in C++. Is Torch the one that's kind of the boost people, or or am I confusing that with something else? Yeah.
It's obviously the basis of PyTorch.
The basis of PyTorch. Yeah. Yeah. So I think, right. So yeah. I think that it's a little bit different, that I think that these are designed for running on CPU, whereas Torch and PyTorch is more abstracted and can run on GPUs and, is expressing things at a higher level. Whereas I think that these tools, this specific type of language, is designed for explicitly controlling the SIMD at a lower level. Because it's interesting, because GPUs, like, basically at the hardware level, there's SIMD that is very similar to CPUs. But as far as I know, there is no programming affordance that lets you write explicit SIMD code for GPUs. It's just the implicit model has just kind of won in that domain. Okay, was there more that I wanted to say here? I think that's about it. Oh yeah, there was one more thing. These portable libraries are kind of janky. Like, they are not, ergonomically, there's a lot of things that are just clunky to use. And one of the really big pain points in Fearless SIMD, in particular in Rust, is that it really depends on inlining as a load-bearing feature to achieve your performance. Like, if the inlining doesn't happen the way you expect, then you end up doing things like crossing over from like an ADI that uses 128-bit vectors into another ADI that uses 256-bit vectors, and performance just kind of falls apart. So there is absolutely room to just, like, I think both just do incremental improvements, like maybe having some finer grained control over inlining. But I think that there is scope to design from scratch a language that is your language, that does explicit SIMD and kind of solves all these problems. Like, people just haven't really put their head around, how do we design a programming language that does a really good job of expressing explicit SIMD and then compiling that to run well on your hardware. So that's one of my calls to action. Go out there, design that language. I want to use it. One of the challenges in SIMD land on CPUs, this is generally not a problem on GPUs. GPUs there's the width of the SIMD vector is a problem. How do you know what that width is? Is that going to be changing? Because different hardware has different SIMD widths. Like, traditionally, ARM has 128-bit widths. Traditionally, most, Intel is sort of in transition from 256-bit widths to 512s. I should say AMD is in that transition. Intel started it, but Intel. And the kind of trendy new thing that's happening in CPU design is this idea of scalable SIMD. And in scalable SIMD, you have an instruction that says, add this vector of numbers to this other vector of numbers, but we're not going to tell you ahead of time what that SIMD width is. It's going to depend on the hardware. So you might write this code, and if you're just saying, add this vector of n to this other vector of n, that's pretty easy code to write, because you just say, chunk it up in 4 or 8 or whatever, and just, keep iterating until you've done n. But if you're doing these more sophisticated things with like cross-lane communication, from my perspective, it's a disaster, right? And so what you're seeing this in newer designs, like it is in SVE2, which is the ARM, like ARM is basically, ARM neon is 128 bits, that's it. You're never going to see wider neon than 128 bit. If you want wider than 128 bit, then it's like, have SVE2. None of that is shipping yet, but SVE2 is shipping on some chips. Like the M4 has SVE2, Apple Silicon. But it isn't at the 256-bit width. It's also a little bit of this chicken and egg problem that nobody's switching to SVE2, and so there isn't any hardware that would actually use 256-bit, and so that's why there's no incentive to build hardware. There's no incentive to write programs on it. And then RISC-V RVV, the RISC vector extension, is the same story on RISC. And I don't know. I have mixed feelings about this, because like, if I want to write assembly code, I can imagine how to write assembly code that uses scalable SIMD. But if I'm writing in Rust, it's really challenging, because Rust doesn't really have a concept of, here's some value, but I don't know what size it is. Like, it has that concept, but those are all like boxed things that live in memory. It doesn't really have, like, here's a vector that's, some width of scalar, some width of floats, but I don't know how many. That's just not a concept that really is in the language. Question.
One of the things, just to clear that it's going to be some power of 2, and then have the compilers figure it out for the hardware.
The question is, why don't you declare it's going to be some power of 2 and have the compilers figured out for the hardware? I think that's the dream. And like, as I say, like, if you're auto-vectorizing scalar code, so if you write a scalar loop that says for I equals 1n, C of I equals A of I plus B of I, that is something that auto-vectorization can do. And you can very easily imagine a compiler that will take that code and lower it to the scalable SIMD. But if you're talking about something like, let's say, prefix sum.
No, but if you know it's some power of 2.
If you know it's a power of 2, that gets you part of the way. And it is true, like, and you know the algorithm to break it. But how do you express that algorithm? See, that's the fundamental problem that's the heart of my talk today. Like, how do you express the algorithm that says, here is all of this parallelism that is inherent in the problem, and I'm exposing that parallelism to the compiler, and the compiler says, okay, I'm going to harvest that parallelism, I'm going to chunk it up so that some of it is parallel and some of it is sequentialized. And what language allows you to express the inherent parallelism? Yeah, the question is the worst case designer. So it's the real truth is that it's very complicated. And the real truth is that a lot of times you want to do optimization. In some cases, and I will get to this, in some cases you'll want to do optimizations where you actually explicitly working with the chunk size is going to help you in a way that the compiler, like, I actually have a line, you'll see it, the sufficiently smart compiler can't do this, and I'll get there. I'll motivate that. Okay. So one thing that comes up a lot, and actually one of the reasons it's coming up a lot, is Rust. Can we just run normal languages? Do we need a new language? Does it make, like, can we just run, like, these days you say Rust is a very, very good language. Like, I want a good parallel language. Rust is a good sequential language. I'm a little bit biased. There are other good sequential languages. Can we just run those on GPUs? And I think, like, CUDA is actually moving in that direction. So I talked about the function pointers, right? Like, that doesn't really work in the implicit SIMD model. And CUDA is like, screw it, we'll just add hardware. And so there actually is a function pointer. It's still SIMD, but it, when you get to a virtual function call, it says, are all of these the same? Well, if they're all the same, then you just do that. And that's going to be very common, right? But if they're different, then it'll the hardware will actually keep track and say, well, I'll do some subset and I'll save the state and deal with the stack and deal with the fact that the stack might be an allocation, the stack size might not be bounded. There's hardware in CUDA. This is relatively recent. This is just in the last few years. It actually goes farther than that. That one of the things that CUDA can do is you can write code, you can write C++ code that will run on both the CPU and the GPU. And you don't really care which side it runs on. And so you say, oh, well, what happens when you get to a virtual function pointer, right? That's a pointer to machine code, right? Well, they have a hash map. So you have the pointer to your CPU code, and the GPU says, that was a virtual function call. I'm going to look it up in this hash map, and this will tell me the address of the GPU code that I'll branch to. So there's a lot of, infrastructure there to support running C++. But fundamentally, I don't think that's not what I want to see. Fundamentally, that feels like putting, an impedance mismatch, right? That, I want to do kind of what Jeff was talking about, of express my parallelism in a very high, express my intent and then have that map, as opposed to having all these like tricks to, to write something that looks like a lot of threads in a scalar language and, have those kind of jammed into running on hardware that's really parallel. The question is, why do I need intent? Why can't I just express? So, yeah, I mean, let me see if I can answer that question. I use the word intent, but it really is expressing the parallelism, right? And, and so that's the fundamental problem. It's like, so if I'm in APL, then expressing the parallelism is easy because I just have these huge arrays. But now I have the problem that I can't express interesting control flow. So maybe the word is just expressiveness, where I know what I want to do, which is intent, and I want to just express that in a language that can then map efficiently to hardware. And I just feel that going through the additional step of expressing it in a scalar language is not what I want to do, because that sucks the parallelism out of the problem. And I want to I'm thinking in parallel, and I want to express it in parallel and have it stay parallel until it gets to running on parallel hardware. But there is interesting work. I don't want to give this up. There's a lot of advantages. You can use familiar tools, familiar languages, port existing stuff, and that's the reason why you're seeing so much investment in this space. And so you have VCC, which is a really interesting research effort to run C on Vulkan, the full C language. I think it's really interesting, but it's also showing some of the challenges. And then you've got, there's actually a new company that just spun up in the last month called Vectorware, which is the people that did Rust GPU, and they're trying to scale up. And there might be interesting stuff here. So this is why the answer is maybe, but it isn't my vision of what I really want to run, how I want to express my programming ideas. The one argument against going through scalar programming model, going through threads, is tiles. And this is an evolution in what hardware can do. And so you have these things, they're called, the marketing language is tensor cores, but the kind of standard Z's for it is cooperative matrix multiply, which is to say you've got these vectors and you're going to do an outer product of two vectors in one machine instruction. So it's very different than your classical SIMD stuff. And generally, until Blackwell, then you would express this at SIMD, SIMD or subgroup level, where you say, okay, I've got a vector, and it's, if you're on NVIDIA hardware, it's 32 floats wide, and so that's plenty of parallelism. But they're just scaling this up, and so on NVIDIA Blackwell hardware, it doesn't fit in one subgroup anymore. The tensor core, the cooperative matrix multiply primitive on Blackwell is a larger multiplication than it fits in a single SIMD vector. And so it isn't SIMD vector registers anymore. It's tensor memory. It's a new memory space. And the operation spans two SMs, right? It isn't just one instruction running on one SM anymore. And there's a lot, if you want more detail, it's kind of fascinating. You can follow that link. And so basically, this is evidence that this scalar thread programming model that CUDA has, executed brilliantly on over what is 15, almost 20 years CUDA's been around, is running out of steam, right? It's no longer adequate to really get the maximum performance out of your machines. And so you're seeing tiles, and you're seeing programming models that are built on tiles, and this is an interesting development. And the way you get to tiles in GPU land, instead of going through this kind of CUDA C++ thing, is it uses this thing called MLIR. And I think of MLIR as being halfway between a language and a library, right? Because unlike a library, you can do transformations, like take two operations and fuse them together, right? So that's something that a language would do. That's something that an optimizing compiler would do. And MLIR allows you to express that. It really comes out of the TensorFlow, JAX, machine learning world, where you have these very rich dialects that have all kinds of linear algebra operations, matrix multiplies, all of the matrix kind of math things, and all of these transformations that do. There's a lot of optimizations that you can do. So you're expressing that intent at a very high level. You're saying, I want to do this matrix multiplication followed by this activation function. And those are kind of, operations in MLIR. And then your MLIR compiler and runtime stack will do a very good job of applying those optimizations, lowering it into what hardware is actually running. The Mojo language, I have Mojo in there twice. Mojo language is basically a syntax layer over MLIR, where you can express, like, MLIR allows lots of different dialects. It's an open-ended framework. It isn't just one thing. And Mojo basically lets you say, if you have, this dialect, then you can just write these operations and then run it through your MLIR implementation. And then there are dialects for the low-level targets. So if you have a specific piece of GPU hardware, there's an MLIR dialect for that, but you're generally not writing that yourself. You're generally writing in these higher ones and using these optimizations to lower it down. So this is something to watch, right? Like Google has a big investment in MLIR. NVIDIA is starting to adopt it as the basis for Qtile. And you've got all these other things out there like Mojo. So this is something to watch. Okay, so the question came out, like, what kind of stuff do I want to write in these parallel languages? And one of the kind of things that I've seen in trying to do these graphics, these 2D graphics workloads, is that a lot of problems out there can be reduced to these monoid operations. So prefix sum. There's actually a lot of variants, like there's segmented sum, there's all, and so I kind of listed this out. But this is the kind of thing that I kind of feel like I should be able to write at a very high level, that I can say I have a sum sequence, and then I have a map operation, which is very much like embarrassing parallelism. That's very much like a shader. I just want to do this scalar calculation, but replicate it over all the elements in my array. But I also want to do scan if my operation is associative. I want to take advantage of the associativity of that operation to say, I can associate this in any way. I can do it in parallel, no problem. And then I want to do other things like filter, right, which is stream compaction. And it turns out the implementation of filter is also just a scan. Like a lot of things kind of lower to scan, right? That's a really key primitive to get going. And then I added flat map in here. And flat map is actually pretty similar to word graphs. It's because the whole concept of flat map is that you call a function, and instead of the function returning one value, or instead of returning like a true false for filtering, it might be a sequence. So you're expanding, you're amplifying the work that you want to do. And so really, when I look at the execution model of work graphs, it really reminds me of flat map from that functional programming world. So this is one of the things I want. I want to be able to write at a very high level. Here are the monoid operations. I want to compose them in these ways that make total sense from a functional programming perspective, and then have that map to hardware. So one of my favorite monoids is for the parenthesis matching problem. And I'm going to step up the speed a little bit. I'm not going to go through this. Line by line, because I think it will take a little bit too long. But I think it's a very interesting story that the problem that you have, and this is a model of things that you get in, like when you're doing a language, when you're doing parsing, you've got, begin and end of scopes, and you need to find those. You have it in 2D graphics because you've got like a tree for blending and you say begin and end pairs, and those are really parentheses. So the fundamental problem that you want to do is you say you've got the sequence of open and closed parentheses, and for each parenthesis, you just want to find the index of what is its match. The sequential algorithm for this is trivial, right? You get open parenthesis, you just push your index. When you get a closed parenthesis, then you pop the index, and whatever was there on the stack, that's the match. You're done. There's a little bit of subtlety to this. Like the stack is unbounded in size, right? It might allocate. Like what if you have a million open parentheses followed by a million closed parentheses? Like a lot of compilers will actually segfault if you try to do that, but it's a valid thing. You have to think about that. So the way you solve this problem in parallel, I want to give you the flavor of how you solve this problem in parallel. And so you do this thing called the bicyclic semigroup, which is modeling, is basically saying, I'm only going to track the matching of parentheses. So anytime you have a balanced pair, an open parenthesis followed by a closed parenthesis, you've got to rewrite that's essentially erasing that. So once you do that, any string of parentheses just really reduces to two numbers, like how many closed parentheses you have, followed by how many open parentheses, because anything else would cancel. And the combination rule is, I listed it out here, that this min of A1 and B0 is basically the number of open parentheses that are consumed by the same number of closed parentheses on the output. So take my word for it that if you have two strings and you do this, this monoid homomorphism, then this is the operation in that homomorphism that corresponds to string concatenation. Right. Yeah, I should have advanced the slide for this. So your input is a sequence of parentheses that are not necessarily balanced. And, this is how you compute that. Great. So then why does this help you to do it in parallel? Well, it basically reduces your problem to binary search. You build up a binary tree. So basically you just take your two pairs and you do the combination and you just go up the tree. You can obviously do that in parallel. It's a little bit log n. You can actually get the log n and back. You can make it work efficient. And then the paper goes into a ton of detail on this. Once you've built that binary tree, you basically scan up to find where is my matching parenthesis. You can basically query just these two numbers, and that will tell you, is my matching parenthesis in there, or do I have to keep going? And then once you find the substring with the matching parenthesis, then you just do straightforward binary search back down, and that tells you your matching parenthesis. So this is the core algorithm. This, by the way, was found in 1985 by Bar-On and Fishin. So like the computer science, like how do you get the parallelism out of these problems like parsing? That's been known in academic computer science for decades. So now the challenge is, how do we implement this efficiently on GPU hardware? And the key is, this is what I was leading up to, that the work group, you have a work group which is 256 items or 1,024 items, and you really want to chunk the problem up into that work group. So you solve completely the parenthesis matching within the work group, and then you stitch them together. And the structure of that is very similar to the way that you do prefix sums. And so we have a very, very, very efficient, it actually comes to a pretty good fraction of just memcopy speed of solving this problem. This was a lot of work, and the code is kind of painful. And one of the challenges that we have when we're implementing this on GPUs is, well, you don't want to just do parenthesis matching in isolation. If you're building it as part of a compiler, you want to stitch it to other stages. You want to combine it with like lexing and then maybe parsing and type analysis and stuff like that, afterwards. So how are we doing in terms of our existing languages? Well, in shader languages, we can express it. That's kind of amazing. Like you can write this algorithm in shader languages and you get it from performance and it's really good, but it's painful. Like this is not fun and it's a lot of code. And, if you do a slightly different variation on the problem, you kind of have to do it all over again. CUDA, there's another implementation by Thomas Smith that is basically the same story as the shader languages. Functional languages do pretty well here. And so there's an implementation in Futhark for the ParaS project, which is a complete compiler that runs on a GPU. And so that's really interesting. And I recommend digging into that if you're interested in how do you run these algorithms that are not kind of your traditional graphics and machine learning workloads. Running a compiler on a GPU. And Aaron Shu, who's doing this project called CodeDFNS, which is an APL dialect, is also a really interesting picture of how do you run these non-traditional workloads. on GPU hardware. But I would argue that this is actually showing one of the weaknesses of array languages, that his implementation is very impressive, but it only works in the bounded depth case, like if you know what the depth is. And whereas my implementation, the original Baran-Fishkin algorithm, works fine for unbounded depths. And, you know, you can't express the efficient algorithm in APL because you can't solve this problem for the workgroup and then stitch the workgroups together. I want to be able to express that. And then in terms of MLIR, I know there's all these dialects and there's tons and tons of dialects for machine learning, linear algebra, but I don't know of any MLIR dialect. And maybe there's somebody that's working on this. Maybe somebody, you know, I'm hoping, you know, somebody will see this talk and say, oh, you missed such and such. I would love to see that. But I have not seen an MLIR dialect that allows you to express this algorithm in, you know, in a way that compiles efficiently. So what I want is I want things to be hard but doable for the author of a library. I want to be able to write a library that does parenthesis matching and say, I'm going to worry about workgroup granularity. I'm going to express this algorithm, do a lot of work to figure this out and be explicit and know something about the hardware that I'm running on. And I would argue there is no way that I can say, here's this problem of parenthesis matching, sufficiently smart compiler, you figure out how to chunk it up into workgroups and so on and so forth. There are other problems that are simpler in structure where you could imagine that, but I'm going to propose that this is one where you've stepped past what a sufficiently smart compiler could reasonably be expected to do. Then when I also want a language that has good abstraction capabilities, I want something at least as good as Lisp here, where once I've written that library, it has all this fancy performance reasoning. It's like, okay, here's a string. I just want you to match the parenthesis, or not maybe a string. I want you to do tokens. I want to have an interface that says these are tokens that you're matching now. It doesn't have to be just one concrete data type. So I'm going to propose in this talk that if you think that you have designed a good parallel language, I want to see your implementation of parenthesis matching. It is a simple enough problem. Like the scalar version is literally 6 lines of Python. So you should be able to express this problem concisely and efficiently in your language. So this is what I want the world to do for me. I want to see better support for explicit SIMD in the kind of Rust, you know, C++ world. I think that there's stuff you can do, like you can have better control over inlining in Rust to make existing languages better, but I also think it's worth trying new ones. If you are designing, I think it is possible to do some of the language design work. I think it's possible to imagine a good parallel language, and then you can compile it to run on multi-core CPUs. And you know that the performance is not going to be great, but there are other things you could do. You could run it on, there are accelerators like TensorTorrent and so on and so forth that you could target that are basically grids of a large number of CPUs with vector units on them. I think you can do some interesting research. And then if you do target GPU, I think the gaps, the missing pieces, the inability to do this medium grain dispatching is going to hold you back. That this is the problem with slang. That, you know, if you're overly focused on running on existing GPU hardware, that's going to constrain what you can do in a way that I think it's at the very least an interesting research program of what can you do if you don't have that constraint, if you have a more powerful execution model. And then the last thing is, like, if MLIR is so great, then we should have a dialect that at least allows you to express the same kind of things that you can do. You can express it in a shader language, but can you express that at a higher level, at the next level up in an MLIR? So I am hopeful. I think we're in a weird timeline for a lot of reasons in which Larrabee did not succeed, and we have, we do not have a good parallel computer, but, things can evolve. The answer to the chicken and egg problem is that they evolved from dinosaurs. And there's a lot of people out there that are doing work on AI accelerators and so on and so forth. Most of that work is extremely focused on machine learning, which doesn't quite address the things that I'm interested in, but it is possible that you just accidentally add the features that are needed. And if you're specifically looking for more efficient implementations of sparseness, when you get into sparse matrix multiplication, you do get this kind of need for this medium-grained scheduling. So I am hopeful. I don't think it will happen soon, but I am hopeful that this will happen. Any other questions?
So, do you think that the mainstream architectures are kind of moving slowly in the Laravel direction by adding simply hardware to this?
The question is, are mainstream architectures moving slowly in the Laravel direction? That is a fascinating question. I think the answer, there's a half yes and a half no. They're definitely moving in that direction in terms of having the capabilities and having the SIMD width go wider and having hardware support for predication. Those are all developments we're seeing. Fundamentally, though, the problem is, can you get the same computation 10 times more power efficient so that it's competitive with the GPU? And again, we're also seeing this movement where we have E-cores now, we have efficiency cores and performance cores. So maybe maybe the answer is that we're very, very slowly moving in that direction. And so if you do kind of an efficiency squared core, that would look a lot like a GPU, but people don't really want them because if you try and run Microsoft Word on an efficiency squared core, the performance will absolutely suck, right? Like CPUs are sold on the basis of how fast they can run single-threaded workloads. And if you try to run a single-threaded workload on a GPU-style CPU, it will suck. Whereas Laravel was kind of, maybe that's like, I don't know, like was Laravel, did it fail because you can't reconcile the need to do well on single-threaded workloads with the performance, the throughput, or did it fail just because Intel executed it poorly? I think a little bit of both, but I'm kind of leaning personally in the latter direction. So that would, if that's true, then there's hope that some future CPU designer would be like, yeah, let's actually make a super efficiency core that really realizes the dream of what Laravel was trying to do.
So, given that there's this chicken and egg problem, where do you think our best hope comes from? Does it come from academia? Does it come from NVIDIA or Intel? Does it come from someone?
The question is, given the chicken and egg problem, where does the best hope come from? Does it come from academia or industry or kind of evolutions of existing products? I think there's scope for a lot of different stuff. Like I think that academic research can have a very large role in this. And I'm looking back to, for example, the incredibly outsized role that the risk research largely at Berkeley had, that really enabled ARM, right? ARM was directly inspired by the risk paper. And so I really feel like if you're an academic researcher in this space, that there is an opportunity, like the chicken and egg problem creates the opportunity to do meaningful work that isn't just going to be done by, NVIDIA coming out with the next generation of the products. At the same time, it is entirely possible. Like, somebody could be designing the next generation of CPUs that want to be competitive with GPUs or just evolving GPUs to say, we want to do a really good job on sparse matrices, so we're going to add this, ability to do fine-grained dispatching, scheduling. And so I think that it could come from a lot of different directions. But the reason why I'm not very hopeful about industry in particular is that there's this, I talked about this a little bit in my Good Parallel Computer talk, the complexity ratchet, that you're additively adding so much complexity. And so part of my dream for a good parallel computer, again, this is like the risk thing, is that you throw away a lot of this complexity. You say there's a fundamental, you're just mixing fundamental primitives of computation and making it go in parallel and figuring out how to coordinate that. And then you layer all this complex junk on top of that. You're basically writing a library for a simple computational model. But the industry trends do not favor this happening, right? You have to compete on how well do I execute existing workloads. And, so I think it is, if I had to predict it, I would say that if this happens in any kind of reasonable time, that academic computer science research will be playing a fairly large role in that happening.
Any other questions?
So if you put any of the AI agents, coding agents to task, you have a very comprehensive goal description. What results have you got?
The question is, have I put AI agents to the task of trying to implement this goal? And the simple answer is no.
The results I predict will be interesting.
That's why you want this. Someone asked before. That's why you want the what was the word? It's a specification. We call it. So that you could just tell the LLM to do it.
Well, this is more than adequate to get some very good and useful results.
If in general, I have found for the kind of cutting edge stuff that I'm trying to do, that I have found AI agents to be not very useful. You know, but on the other hand, they are getting better. And I know there's a lot of, I didn't wear my anti-AI shirt. I should have. I'm an AI skeptic, in case you hadn't guessed that already. So, but yeah, I mean, you know, I have a more nuanced view. I think that there's some domains, like, you know, I gave a talk at Google about a month ago, and, you know, I was talking about not this problem, but other problems like migrating C++ code bases to Rust. That's something that AI can do amazingly well at, right? And there are reasons for that. I won't go into all that now. But here we are, you know, you have to draw deeply from an understanding of like physics. And AIs just don't cross levels like that.
Well, so I'm an AI maximalist, and this is
Okay.
exactly the frontier that I'm working on. And I don't think it's physics. I think it's computational theory.
Computational theory, yeah.
And so that's why, and I'll probably show again on the Levien talk,
Great.
my ACL2 kernel.
Ah.
So ACL2 is the most industrial spring prover on the planet. And
Yeah.
it does things like improve the mathematical correctness of VLSI.
Yes.
And so
I mentioned ACL2 in my Rust talk at Google as the kind of thing that AIs could be very good at, because humans suck at the tedium of just blatting out a huge ACL2 proof. And if an AI can do that, then I think that's incredible. So yeah, I would, you know, basically what I would say is that I am personally not very optimistic about AI, but if you are an AI maximalist, then I think that this is an incredible problem. Like, this is one where you can really show, you know, the rubber meets the road. Like, if you can actually build these things with AI, then that's a huge win.
yeah, your point is absolutely correct. If you use LLM to do logical inference, you get garbage. So you use the right tool for the job,
Yeah.
which is you use tools that are powerful in computational modeling and logical inference. And like I say, being old school small AI guy,
Yeah.
I just think ACL2 is at the top of that. All the kids all like Lean 4, but I'll point out this: you can't write a quine in Lean 4.
Okay.
All right, everyone. Well, that's all. Thank you, Ace.